Welcome everyone. Today we're going to start by talking about the midterm, get some of the details out of the way so that you can worry about that and stress about it. The good news is we're making great timing. I've never gone this fast in a semester. And so I want to do a quick mid-semester check to see the state of students and where you guys are. And then also, of course, let's talk about the midterm. Today I want to talk about Big O notation, at least to introduce it some more. We'll be covering Big O notation pretty heavily. It will be on the midterm as well. And that will complete everything I need to get through the first half of the semester. I like to make sure that if I do a lecture that it has at least a good week to set in. So the soonest I could start doing the midterm would be either Friday the 29th or Saturday the 30th. Or I suppose I could start it on Sunday the 1st, July 1st. The idea of my exams is that I give you a full week to go complete it. The exam itself is about 2 hours long. If you know what you're doing, you can get the exam done in a half hour or less. If you don't know what you're doing, this gives you plenty of time to ponder why you don't know the things you should know. It should be a life-changing experience for you. If I've never had a student genuinely miss questions because they needed more time. There's plenty of time on the exam. It will be at any authorized testing center, so it won't be in class. You just go find a testing center. For those here in the Wasatch Front, in the Ogden area, just go find a Weber State testing center. They're all over. There's what, 2 or 3 up at Ogden. There's one here at Davis. There's one out in West Roy by the gas station out there. I think there's a pizza place right next to it too. You can go get some pizza, go take your test. That's a great one to do tests, I hear, because it's never like if you're on midterm or final exam, go take your finals out there. You can always just walk right on in. If you're out of the area, you can do what's called an authorized proctor. It's like you pay like a $10 fee. They will help set up a test for you. There's thousands of these worldwide. I've had students in Afghanistan take my tests. So if for any reason you set up and this happens every semester, I get one. Hey Brad, I set up a 2-week cruise right over your midterm or final exam period. Please accommodate me. If you are planning a giant long vacation, you need to let me know right away if you can't take it during the final exam week. That said, the exam itself, I'll get a study guide out for you. We can talk about it more on Monday. Unless you want to talk about it right now. Yes?
Is it more like a big single program ourselves? Or like
It's a mix. I have anywhere from 15 to 25 questions. I like to do some multiple choice because it's faster for me to grade those. I like to do a handful, on average about 3 programming questions. Some free response, in other words, just explain in your own words what's going on here. And the programming one, I'm nice. I don't copy and paste and say if it doesn't compile, you fail. No, I know code. I know what people are thinking when they throw code on paper. If you have a general idea, if your strategy is correct, I give you points. And if the syntax is way off but the strategy is perfect, you can get full credit. I've even given people credit for having perfect strategy written up in comments and providing no code. Yes?
I hear the CAI test is actually working on developing a code
No,
interpreter.
they're working on doing a lot of things, but I'll wait till I see it. I'm actually working with them on a completely separate module of their site. So they've got a lot of plans, but I'll believe it when I see it. The exam, again, is not meant to be killer. It's not meant to destroy your life, make you feel terrible. It is simply meant to assess. There's a real problem in the academic world that assignments don't necessarily assess ability. I have had many students turn in assignments that are 10 out of 10s, and then they go to take the exams and they get 40%. And it's not because they have some kind of test anxiety or some mental disorder that makes them forget. No, 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 no. Tests assess, and they assess accurately and fairly. And if you don't know it at the exam, it just means you didn't know it. And so if I had my way, I would make exams worth 100% of your grade. But I know how much stress that puts on your lives, and I know how rough that is. That's why the exam scores are what they are. But again, it's just meant to assess. If I've talked about something numerous times in class, you can bet it's going to show up on the exam. I do not throw tricky, weird, gotcha questions. That's what the quizzes are for. So I'm not going to throw a question at you that says, we learned about topic X, Y, and Z. If you were to extrapolate those topics and come up with a brand new topic, how would that work? I won't do that to you. It's all, look, I can prove to you that we've talked about this thing 5 times. I'm testing on it. Does that make sense? It's just meant to say, this is simple. In fact, I even throw a handful of 1410 questions in the exam just to help my self-esteem. Because when students miss my test questions, I feel terrible. But then when they miss 1410 or even CS 1400 test questions, I realize, okay, it's not me. These are questions from last semester or 2 semesters ago. If you're missing those, it's not my fault, as much as I'm trying. Other questions on that so far? Yes?
If it's multiple choice, are they going to be all automatic or?
There's a mix. Some of them are choose all that apply. And the scoring system on that is, for everything you get right, you get points. For everything you get wrong, you lose points. So if you check something that shouldn't be checked, you lose something. And vice versa. If you don't check something that should be checked, you also lose some points. I've got an old study guide. I can pull it up here. We can look at it quickly. And we also have a opportunity this semester to do a study day if we need to. Now, study days are weird. Don't think that you can just cram in and learn an entire semester's worth of knowledge in a day, but we can take a moment to say, let's go ahead and verify, do we understand this, and take 10-15 minutes to really go over the topic again. Here is the previous semester's study guide. So I want you to do just no basic object-oriented programming in C++. If you can't write a class in C++, you're in trouble. There's a few things that I have added. We're going to talk more about L values and R values today. We've had a lesson on that previously. That's the whole std move thing. There's some others. Know what inheritance works, constructors, destructors, static. I don't necessarily test heavily on these. These are just things you should know. Difference between stack and the heap. What are C++ arrays? How are they managed? How pointers and arrays are 2 ways of working with the same thing. Know the difference between regular pointers, shared pointers, and unique pointers. I might throw in weak pointers onto this. What's an iterator? Work with linked lists, write code for them. Work with stacks, work with queues. Work with hash tables, how fast can they be? What's big O notation, and so on. So I can get a cleaned up study guide out for you on Monday. Are there any quick questions though on the study guide? You're itching to know immediately. Should probably check the online students, see if they It's Caleb, the coding session is more like, here is a method. I want you to write this one particular method. Or here is a very, very simple class. Make this simple class do these 2 things. I'm a fan of applied knowledge, not on memorization. There will be no fill in the blanks. My all-time favorite, or most hated test question strategy is to pull a sentence from a textbook, strip out one word, and then say, all right, tell me what this word was in the textbook. Oh, I hate that. You will never see that from me. Other questions on it? All right, let's get the dates figured out. Again, I'll give you a full week, or in other words, 7 days. Would you like to go from a Friday to a Thursday, a Saturday to a Friday, or a Sunday to a Saturday? Sunday to Saturday for most people. It usually is the winner. You don't want to end on a Friday night. or a Thursday night. People are working. So we can go July 1st through July 7th. I don't know if any testing centers open on a Sunday. There's got to be some around the world somewhere. I don't know what. I hear Lagoon's open a lot on July 4th, though. That's a great. I know. I'm just saying that. That's a great place. Let's see. Weaver State Testing Center. I'm a terrible father. Every time I see my daughter, she says, "Dad, I haven't been to Lagoon yet. All my friends have been. What's wrong with you?" It's on my mind lately. Make sure you check the times on these. Saturdays, they close earlier than usual, 4:30 p.m., and you have to show up usually like an hour early to make sure you can't just show up at 4:30 and say, "Hey, I want to do my test." They might let you, but they'll only give you 1 hour on the test. Here at Davis, is it also 4:30? It is. So there's the Union, Student Services, and the library. And Tracy, are there 4 up at Ogden? No. Why do they have so many? Doesn't make any sense. Library is 4 p.m. Tracy Hall, 4:30. West, 1:30.
Where is he, guys?
3500 West, 5600 South. There's a gas station right over here. Ace Hardware is right behind it. Yeah, Domino's. Morgan has a testing center. Only open 2 hours on Saturday, but just make sure that you know that yes, it does close. A lot of these close early on Saturdays. Don't show up at 8 p.m. on a Saturday. It's on KaiTester. I can give you a piece of paper at the testing center which you can use only for scratch purposes. You cannot walk in with any notes of any kind. But you can have a piece of paper so you can try to write the program on paper or draw out a linked list and make your code work or whatever it is. Yes?
So is this going to be at every testing center? Because I've had it where the professor said it was going to be at every testing center, but it was not at the library testing center.
I will, if that ever happens, you can rightly come complain to me.
Okay.
And I will make accommodations. I have never had that be a problem. I've set it up to work everywhere and it has worked everywhere.
So if I show up on Sunday and it's not at
So is the library one open Sunday?
Yeah, it looks like it was.
1 to 4.
Where is it in the library? I think I've stepped in there once.
First floor.
Upstairs.
First floor.
There's nothing
First
at all.
First floor. Okay.
So first floor is the final answer.
First
Yeah.
floor.
Okay.
Room 1 is the library.
To the left.
All right, so we'll do July 1st to July 7th. Any other questions on the exam? All right, let's talk about homework assignment. Who is not done with it by raise of hands? 1, 2, 3, 4, 5, 6. Almost most of you. 7. 8. So a lot of you. Where are you guys stuck? Just plugging away, crashing. How many of you? I've changed it up. How many of you feel that you've put in a good effort, that you started early, you put in a lot of time early, and you're still not done? Because a lot of you who are not done are starting it today. I've had a handful of panicked emails I've received. Hey Brad, I'm just starting the homework assignment right now, but I need to I need you to answer these questions for me.
So it's Sunday.
So, all right, I want to not have this lecture be a long lecture. I want to keep it a bit short so that we can make sure we have more lab time here. So let's jump into Big O notation. Let's do a new page here. Why do I keep losing the chat students? I've always mentioned that if computer science students across the country have a shared list of topics they must learn, it seems that 2420 has half of those topics. In other words, CS programs across the country have differences. We are definitely a very applied institution. We like to focus towards industry, not so much towards research and publishing. But even in that case, there are still similarities between our program and a strong research academic institution, which does not focus on business. And again, Big O is one of those commonalities you will see. You must know Big O to be a CS student. I would be a fan of an exit exam. You want your diploma? Answer these Big O notations. The idea behind Big O is that it gives us, oh boy, it gives us a metric to compare various kinds of algorithms to each other. Or in other words, frequently people will say, hey, I've got this wonderful algorithm, or I've got this awesome new data structure. It does this and this, and it's fast this way, and it's fast this way. And there's so many details, and you can't understand exactly how it's structured, how it works. And so your question is, you know what? I just want to know how this thing scales. What happens if I throw a lot of data at it? Will it go slow? Will it go fast? And why? And it turns out that Big O notation is a great comparison metric when an algorithm or data structure scales high. And I'm not talking about scaling to 100 or scaling to 1,000. I'm talking about scaling to millions, billions, trillions if we can. Anybody can write a sorting algorithm that sorts 10 items. That's not hard. Can you write a sorting algorithm that sorts 10 million items and do it in a way that you don't have to let your computer run overnight to do it? That takes a bit more work. How do you know if your algorithm will run fast or run slow? For example, let me show you one such algorithm that sounds interesting. Where do I want to find this at? There's a great animation here of an interesting looking, come down, where are we at? Not you, this one. Here's an animation, let me zoom in on this. View image, zoom in. It's going to sort some numbers for us. And so far you look at it and you say, okay, it's sorting in halves, that's making sense. Maybe it's merging them together. And this is about where people give up. It's sorting, I promise.
Is that merge sort?
No, it is not. It is a block sort. It's a newer sort. So it got the job done, but it was really weird how it got there, right? And it's one of those that if somebody were to try to explain the algorithm to you, you would just say, I don't get it. And I'll be honest, I still don't get block sort. It's crazy, it uses a lot of code, it uses a lot of strategies. I'm sure if I spent a couple hours I could understand what they're getting at here, but I don't understand it. So do I understand how this thing scales if I don't even understand the algorithm? What happens if I throw 10 million items at it? Will it go fast? Will it go slow? Do I know? Big O notation is almost like this common language that everybody across the world understands for CS students. So again, if someone would come to me, hey, here's this awesome block sort algorithm. And I would just mutter, oh, Big O, what is it? And they would tell me a Big O answer. Oh, this guy is n log n. And I'd nod my head and say, yeah, that's a good one. I like it. Even if somebody speaks French or Chinese or German, we all know Big O. It's our common mode of communication. And I think a better way to show why Big O notation can be handy is through Have I shown the clock game on Price is Right yet? I'm going to show it again. Which one? Did I show this person? Oh, we got more ads.
$193.
Higher.
$540.
Higher.
$820.
Low.
$700.
Higher.
$749.
I'm going to have to sit down and regain my composure after that. I hope you realize we are in the presence of a miracle.
All right, so what was her strategy? Was it sort of a divide and conquer strategy? Was it perfectly executed? No. Was she exactly doing halfway every time? No, but did she still divide and conquer? Did she get there? Yes, even if she breathed in and went slowly and took her sweet time. She got there. Now, of course, there's the other guy. Price is Right clock game. Now, I've shown you this one before, but we'll do it again. So let's...
$15, 50. I'm sorry. All right. $50. You say. I will say higher, and they'll start again. 55. Higher. 60. Higher. 65. Higher. 70. Higher. 75. Higher. 90. Higher. 95. Higher. 100. Higher. 105. Higher. 120. Higher. 125. Higher. 150. Higher. 160. Higher. 200. Higher. 250. Higher. 275. Higher. 78. Higher. 79. 80. 81. 82. 83. 84. 85.
I love his response.
Do you think you're doing... Look, this is that... William... Starting at $50 on that baker's rack, that's a $701 prize over there. And you're down here with these...
All right, so what was his strategy? Increment by ones, fives, tens. Was he faster than the previous contestant? Well, no, did he spit out numbers faster? Yes. Was he going to get to the answer faster? No. So we have a difference of algorithms, and we need to be able to quantify which strategy is faster and why. You had a question?
What was it, the item he was going for here? Was it just the rack?
It was a baker's rack.
I can understand why he would start at 50.
Well, I mean, I don't understand though why he would go by tens, and he doesn't know the divide and conquer strategy.
I would do about higher than 300.
Boy, what?
Or that side.
What if we didn't just do the clock game with some price between, say, $0 and $2,000, but I wanted to do the clock game between $0 and $1 million. Now, how can we extrapolate or get a feel for how long it will take the lady versus the older guy to get to their answers? Can we compute it? Can we get a feel for it? Do you know how to come up with this answer right away? If you were to say right now, divide and conquer, for $1 million, between 0 and $1 million, how many steps would it take the lady to get there? Just give me your best estimate that you just thought that went through your head right now.
What is it, called?
And just tell me a number. 35 steps? Anybody else? 10,000 steps? 100 steps? So we're dividing and conquering. I got a pretty wide range here. Somewhere between these. 100, any others? You get the idea. You're trying to make a guess. How long would it take the older guy to find the correct answer if the number was between 0 and $1 million? and he was counting by 5s or 10s. How long would it take him to get there? Give me your quick estimate that just went through your head. 200,000 times. No, on average. Let's say it's a random number. We don't have Joseph with his D20 ring. Let's say it's a D1 million ring. You know, or you can ask one of those Google or Amazon Echo, roll a dice for me, and it does it. And so the older guy's a little bit easier, correct? You would say, well, take the number, and I'm going to divide it by whatever his separation is. He's separating by 5 every time. Okay, well, there's a million. And chances are he's going to get to it halfway, so 500,000. So we go from 1 million, but we think that the chance that he'll get it halfway is, we expect him to get to the answer on average halfway, so we'll say 500,000. And if he skips by 5 every time, then he needs to take 100,000 guesses, correct? All right, but what if we divide and conquer? What will happen? Give me a number, an exact number.
180,000.
How do we get there? Well, it's not too hard to figure out. And we're going to take a moment to understand this, and you do need to understand this concept. So let's say we start, if I say I'm thinking of a number between 1 and a million, what should be your first guess? 500,000. And I can tell you higher or lower. Now there's going to be 2 possibilities, correct? Well, there's 3. You either got it, or it's smaller, or it's larger. So here there's one, you've hit one number so far. It could go smaller or it could go larger. Let's say I said smaller. Then what should be your next guess? 250,000. But if I said larger, it would have been 750,000, correct? So now we are at 2 more guesses. So we have now covered effectively 3 possible guesses out of a million. Let's say it is now larger. What number should you use here? 37,000 or 375,000. But it could have gone a total of 4 ways in my branching, correct? And then if I said it's smaller, you would have come up with a new number. But in reality, you have to understand that now we have an 8-way branching. Does that make sense? So there was 15 possible values up to this point. So here was 1 value, here was 3 total, here is 7 total, here's 15 total. And you can see that this branching is going to keep going. 16, 32, 64, 128, 256, and so on. Meanwhile, what is this number going to be right here? The previous number minus 1, correct? So 31, 63, 127, 255, 511, 1023, 2047, and so on. I could represent this by a level number. What tree height are we at? We are at a height of 0, or so I will say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. Is there a way that I can take a number here and compute that number there? Is there a mathematical expression that lets me get there? Yes, what is it? It's actually a pretty easy one. How do I go, give me a very simple expression that I could take a 9, plug it in, and I get out a 511. Well, how do you get this number? Let's go with this column. What's an expression that gives you that number? No, that gives me anything in this column. If I have a 9, I can get to a 256. This is, you can see these are squaring, correct? And this is effectively also the same square as just subtracting 1. So if you take the column number n, you square it, and you subtract 1. In other words, if we go to n,
I think I meant 2.
if I take n squared, or no, you're going to take 2, yeah, you're right. 2 to the n, subtract 1. Correct? What's 2 to the 10th? 1024 is 2 to the 10th. Subtract 1. 10,023. Make sense so far? All right, so we're doing pretty good. I can keep growing this thing. How many possible numbers are there? In my original number guessing game, how many possible numbers were there? In other words, I can go 4,096, 8,192, and I'm going to keep increasing that number, but when do I stop doubling my numbers? When I pass over 1,000,000, correct? At that point, I have guaranteed that my number guessing game has divided and conquered enough, and I have to have found the answer by now. Would you agree? How many n steps is it when I can guarantee that I have definitely hit the answer by that point? Well, that's simple as solving. 2 to the n minus 1. When does this roughly equal 1,000,000? At what point, at what point is 2 to the n minus 1 going to cross the 1,000,000 threshold? Well, so how do you solve for n here? Okay, we're going to add 1. 2 to the n is roughly 1,000,001. Oops, too many of them. Yeah, for those of you who've forgotten, some of you have remembered your math class, a lot of you have forgotten. Let's do a review here. 3 plus n is equal to 10. How do you solve for n? Subtract 3 to both sides. All right? So this is subtract. What if you have 3n is equal to 12? What do? You divide. What if you have n squared is equal to 16? What do? You square root. What if you have 2 to the n is equal to 16? What do? You don't nth root, because you still have to solve for what that n is. You log base 2 of that thing. So I would log base 2 of 16. And that would give me my n. So if you ever have to solve for an n in an exponent, your opposite is log. And you have to do log base of whatever the thing was, of whatever power was raised to.
Calculator-wise, that's log number divided by log 2.
Yeah, that's easy to put into a calculator. Any questions on that so far? All right, so I'm not going to worry about this exact one. I'm just going to say, what's log base 2 of 1,000,000? Well, let's go to good old Wolfram Alpha, the one company that I am shocked that Google has not bought yet. Seems like everything that old school Google would be about. Log base 2 of, I can even say the word 1,000,000. That's how awesome they are. And where's an answer? Where'd it go? Oh, there we go. Roughly 20. 19.9. So, if that lady did perfect divide and conquer, how many steps would it take for her to guess the correct answer if the number was between 1 and 1,000,000? 20 steps. Could she take her sweet, sweet time and get there? Yes. Would she still get faster than the guy? The guy was going to take how much? We were thinking if he was counting by fives, 100,000 steps. She takes 20, going nice and slow. What algorithm is better? Divide and conquer or incrementing by 5? Yes, in fact, the best guess I got on the divide and conquer was 35. And in reality, the real answer is 20. That's pretty good. What if the number guessing game was between 1 and a billion? Now how many? Well, let's take log base 2 of a billion. It's 30. How about a trillion? 40. Divide and conquer is fast. It is nice. In the big O world, I would describe divide and conquer this way. It has a big O notation and it's written this way. Big O of log of n. Now it's weird, it's a weird notation. Where did the base 2 go? Why do we have this O in parentheses? What's going on here? I won't get too much into the details of why this big O is here. It has a mathematical definition which helps it say what is it bounded by. The base 2 was dropped out because you get the rules of big O notation is that you are more interested in what class of family it's in, not so much some of the constants involved. We'll see that showing up more and more. So I will simply say that divide and conquer is a log n algorithm. If I wanted to get really picky, I'd tell people it's really a log base 2 of n, but that's not what big O notation is about. In computer science, it's usually base 2. But we'll deal with some trees later in the semester where we'll be base 3 or base 4 or base 5 or base 1,000. We okay so far? All right, let's learn some of the common families of big O notation. Now this is not exclusive, or it's not complete. It's not exhaustive. You can come up with any strange looking big O notation so long as all the variables are independent and it fits your data according to your analysis. For example, I think I had where did that sorting algorithm go? Let me show you some of these right off the bat. It's a good listing of a bunch of them. Here's a bunch of big O's. They didn't write O parenthesis, they just wrote the inner parts. See some commonality showing up in there? N squared, n log n shows up. Here's a weird one, n to the 4/3. Are there any other weird yellow ones? Plain O log n log squared n. Then you start having more interesting dials or knobs or things that you can tune into the algorithm itself. So now you have more independent variables that get involved in your data. So now we have n plus r, n times k divided by d. Here's a weird one, n to the log base 3 divided by log 1.5. We'll get to BOGO sort. N factorial, infinity. And I've seen some really crazy, let's see if I can find this one. Big O matrix multiply algorithms. Someone's got to have a table of these. Will Wikipedia have it? Here we go. Let's zoom in on this. There's something called matrix multiply. Have you done your discrete math class yet? Did you have to do a matrix multiply problem?
Yes.
Some of you have, some of you didn't. How do you multiply matrices together? It's normally that the one everybody assumed is that, oh, it's just always n cubed. And so what they're showing you here is the exponent of n. Up until about 1968, we all thought, yeah, it's the exponent is 3. And then somebody came up with a clever method, which is more like 2.81. And people were improving on it. and then improving, and then improving, and then improving. And now they're at the point where if they can shave 1,000th of a number, or like a fraction of a percent on that n, they're mathematical heroes for a few years. It's going to hit a point where it's not even practical anymore. People are starting to abuse big O notations rules just so they can make this chart and claim that they're awesome. But we'll go into more of the details of it. All right, so let's go over common big O notations. The most common algorithm is a single loop. It has a big O notation of n. In other words, if I'm looping from 0 to n, how many times will that loop iterate? N, right? It's a very straightforward question. So the idea is to say comparison. All right, well, I have 1 billion items of data, and I want to put it into your algorithm, which is big O of n. How many steps can I expect the algorithm to take? Somewhere in the billion range. Makes sense so far? I knew it was a single loop, and it's just looping on n. It's nothing straightforward or fancy. Big O is n. Now the next most common one I'd say is a loop within a loop. Let's say the outer loop loops n times. The inner loop also loops n times. How many times will the inner code overall process? In other words, let's simplify it. I have an outer loop from 0 to 100. I have an inner loop for 0 to 50. How many times will this one line of code run? So it runs the inner loop 50 times, and then it goes out and increments the outer loop once. Then it goes back and runs the inner loop another 50 times. Then it comes out, increments the outer loop again. 5,000. How did you get the 5,000, Joseph? You multiply them, right? So a loop within a loop is typically the whatever the size of the outer loop multiplied by the size of the inner loop. For simplicity, I will assume that both loops are the same size. Therefore, that loop is an n squared, according to my big O notation. Let's actually do some example numbers here as we write these down. Suppose my n is 10, 100, let's do 1,000,000, let's do 1 billion. We won't go to 1 trillion. Oh, let's do 1 trillion. 10 to the 12th is 1 trillion. All right, this is very straightforward. How many steps roughly do we take our big O of n to take if I have n or 10 inputs? What do I expect here? It should take 10. This one should take 100. This one should take 1,000,000. This one should take 1 billion. How about if my algorithm is n squared? How long do I expect these to take? What's 10 times 10? 100. What's 100 times 100? 10,000. You can start counting up zeros. There's 4 zeros here. What's 10 to the 6th squared? Do you remember how to do that math? What do you do in this rule? You multiply those two numbers together, so it's 10 to the 12th. What's 10 to the 12th squared? Some ridiculous 10 to the 24th. What is that? 10 to the 15th is... 12th is a trillion, 15th is a quadrillion, 18th is a quintillion, hextillion, septillion. So please do not do a loop within a loop on 1 billion items. That will take a while. Other algorithms, we just covered divide and conquer. What was divide and conquer's approach? Or what was its algorithm? Or big O? It was log of n. What is log base 2 of 10? Or log base 2 of 100? Let's go grab some of these numbers real fast. Log base 2 of 10, 3.3, how about of 100, 6.6, how about of a million? We just did that one, it's roughly 20. How about of a trillion? We did that one also, it's roughly 40. Make sense so far? You throw a billion or a trillion items at a login algorithm, we should expect it to take 40 steps. That's nice. There's another one. This one actually shows up more often than you'd believe, or you would recognize. No, oh, how do I say it? Just straight code. I don't know a better way to describe this other than there's no divide and conquering, there's no looping, you're not calling itself, it's just a bunch of steps. It's serialized code. A goes to B, goes to C, goes to D, and you're done. Yes?
Does that table show like how many steps it takes?
How long it would take to what?
How long each loop, how many steps it takes? Is that what this table shows?
It's not showing exactly how much each loop takes, it's saying if you had an algorithm that had this amount of inputs, if that's your inputs right here, here's how long we expect it to take. Does that help? I'm going to move this up here. Hold on. Grab, move. So I am highlighting this not for participation code reasons, just so you know those are inputs. So when I say straight code, maybe I'll call it serial code. There is no looping, there's no calling functions, there's no recursion, there's no dividing and conquering. It turns out in this situation, it has a really weird looking big O notation, big O of 1, because it's not dependent on n. If I had a million items, it might take 5 steps. If I had a billion items, it could still take 5 steps. So we just say I'm not even caring about n, it has nothing to do with n. So I will just simplify it and say it's in the range of a step. It might, and we'll talk about, big O is meant to kind of be we'll get back to that. It's not meant to be a exact amount. It's meant to show a family that it's in. What is it asymptotically approaching? We okay so far? Yes.
Serial code basically is like saying like n equals 1.
A serial, yeah. I'll give you an example of serial code. Our hash table that we just did. Let's say I have 1 million students, but I have 2 billion buckets. What was the process? You take a student's ID number, then what? You hash the ID number. Does hashing the ID number have anything to do with the amount of students? No, it's the same hash whether it's 1 student or 1 million students, correct? You hash the W number, or the ID number. That's not dependent on the amount of students n. Then what? You mod by the amount of buckets. Is that dependent on the amount of students? No, it's just a mod. It's a math problem. That's easy to do. Then you go to that bucket. Is going to a bucket expensive? No, you go to the bucket. Then you hunt down the bucket to see if you can find a matching key. Well, if you have more buckets than students, you're almost always going to get it the first try. So, was any of those steps dependent on the amount of data? No, you hash the key, mod the key, go to the bucket, look at the bucket and make sure the key matches. Whether it was 1 million or 1 billion, it's the same. So a good hash table we can say has a big O of 1 amortized. Does that make sense? All right, some other ones. A serial code is an algorithm. It's just not. Hash tables have used algorithms. It's just not an algorithm that repeats itself. A lot of sorting algorithms. No, let's do a loop within a loop within a loop. Loop inside of a loop inside of a loop This is matrix multiply. What's its big O notation for the naive case? N cubed. All right, so what's 10 cubed? 1,000. What's 100 cubed? You have 2 zeros. So that'll be 6 zeros total. 1,000,000. What's 10 to the 6th cubed? 10 to the 18th. What's 10 to the 12th cubed? 10 to the 36. Let's keep going. A very common algorithm is loop to divide and conquer. I gotta cram this one in here. Inside a loop, you do a divide and conquer step. These show up all the time. Most often, sorting algorithms. You saw that on the sorting algorithm page before. There was a bunch of n log n's. If a single loop is n and a divide and conquer is log n, and I'm putting a divide and conquer inside of a loop, it's like I multiply them. So that's where I get the n times log n. Make sense? Loop is n, divide and conquer is log n. If I'm doing a divide and conquer in a loop, I multiply them, n log n. So I can figure out these values by multiplying these two together. This is 33, this is 660, this is 2 times 10 to the 7th, this is 4 times 10 to the 13th. Some large numbers there. All right, let's go to some of the more silly, yes?
Mathematically, which one would you first? The log n first or the n?
Yeah, they're multiplying, so it doesn't matter. What is that property? Associative, commutative? I forget what that it doesn't matter. It multiplies. There are some other common big O's which are 2 to the n. This is often called a brute force, where you try to find every possibility that exists. For example, if you're trying to call somebody up on a date and you've tried to plan out every scenario. If they say yes or no, I'm going to have the conversation go this way. If they say yes or no to these, I'm going to go this way. And you try to write out all your scenarios. It's 2 to the n. Another common 2 to the n is a naive traveling salesman problem. Have you heard of that problem before? Here's the problem. Salesman is traveling around town. He has to make 100 stops. What's the most efficient route for him to go make those 100 stops? It turns out that is not an easy problem to solve. The brute force way is just to say, you know what, let's just look at all 100 possible routes, or all possible routes, all permutations, to see where we can get to. And what possibilities? We go here, we go this way, we go this way. What is 2 to the 10th? That was 1,024. What's 2 to the 100? Is that a big number? How big? No, I got, Wolfram Alpha will do it. 2 to the 100 is 10 to the 30th. That's big. What's 2 to the 10 to the 6? What's 2 to the million? 2 to the 10 to the 6 is 10 to the 301,000th power. Are these big numbers? These are so big that I'm actually going to write it in this expansion. 10 to the 10 to the 5.4. Whenever you see exponents with exponents, then you know you have a really big number. What's 2 to the 1 billion? Or 2 to the trillion? Oh, I know I didn't break you, Wolfram Alpha. I probably just lost my internet connection.
No, it just doesn't want to calculate that.
It'll do it. Oh, where did it go? Oh, I forgot. 2 to the 10 to the 12. Is it not going to do it? I've never done that before. All right, 10 to the 10. It's big.
Big enough that
Now there's another one. I will call this the worst possible algorithm. And I throw this one in here just for fun. And this was the BOGO sort one that we saw earlier. N times n factorial. Here's the BOGO sort. Imagine you had a deck of cards. They didn't have suits on them. They were all unique and they had numbers 1 through 52. And you want to sort those cards. They're shuffled. So here's your strategy. Throw them in the air, let them land on the floor, gather them up, and check if it's sorted. If it's not, repeat the process. How long will that take? N times n factorial is the representation for it. How bad is this scale? 10. I mean, you could get lucky the very first try, but even if you had 10 cards, it will take 36 million attempts. Or there's 36 million possibilities here. How about if you had 100 cards? Oh, these are big numbers. Nine times 10 to the 159. Will it take a million? And no, it's not going to take a trillion. 10 to the 6th times 10 to the 6th factorial. Will you take it? Will you take it? It did. 10 to the 10 to the 6.74. No one ever bothers to check it. No, there's enough mathematicians out there that are geeks. They will double check it. All right, now let's put this in perspective of what a computer can do. How many calculations roughly can your computer do a second? Use the gigahertz as a rough guide. Somewhere in the billion range, correct? Right, and there's some strategies you can use where computers can do if you do it right and all your computations are independent, it can do, you have multiple cores, and each core can then do multiple instructions at the same time. There's tricks you can do, but you're right, it's on the order of 10 to the 12th, 10 to the 13th. Maybe 10 to the 14th if you're stretching it. That's not too bad, it's decent, right? Where does that put our modern computers? What range are we okay with? This is okay. Surprisingly, the divide and conquer, yeah, sort's okay. Sorting a trillion. It'd take a while, but we'd get it done. Here, 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 here. Anything in this range, our computers can do. Make sense? So what if somebody comes to you with an algorithm and you have a million items? Should you, it's an n cubed algorithm, you have a million items, should you run that on your computer? No, why? It's going to take a long time. No, it'll try, it'll just take a long time. How about supercomputers? What can they do? Well, the newest one, I'm going to have access to this soon, I'm excited. Summit, just got done. There's a new supercomputer. It does 200 petaflops per second. A flop is a floating point operation. So, like you take it's very common in scientific computing, a float times a float. That's a floating point operation. Does that make sense? You rarely work with ints. You work a lot. Well, you work with a lot more floating points than you do with actual ints. So 200 petaflops per second. What's the peta world? Do you know how peta works out? Scientific prefix. What do we have? Peta, giga, mega. You know, megabyte. Let's go down these. We'll learn them. All right. Mega, 10 to the 6th. Giga, 10 to the 9th. Tera, how much? 10 to the 12th. This is about where our computers are. We're maybe in the 10 teraflop range. Maybe 100 teraflops, somewhere in that range. How about peta? 10 to the 15th. Where were they at? 200 petaflops, so that puts them at 10 to the 17th. 2 times 10 to the 17th. The big goal right now, the big push in the supercomputing world is to be the first person to get to 10 to the 18th. There's one, it's called Aurora, it's under development. The United States will have one soon. It'll be using hopefully an Intel Xeon processor. They keep changing the plans on us though. Chinese are going to get there first. You might think, well, why are we falling behind? In my opinion, because the Chinese computers are dumb. They're really bare bones. They're ridiculously hard to program for. The American computers are very friendly. Developers can run almost any kind of C++ code on them, and they work. Whereas the Chinese computers, you have to code very explicitly to that specific kind of hardware, and it limits what kind of problems you can do. But they're going to have a nice badge saying, we were the first exaflop computer. Americans will say, we're the first practical exaflop computer. Who's right? You guys could argue about that. So where can supercomputers get to? They can do somewhere in the 10 to the 17th a second if you do it perfectly. Now, to give you another example, we ran some simulations on the previous supercomputer out at Oak Ridge. The one that we just saw, Summit, is replacing one called Titan. We ran some simulations that took about 2 total weeks of that supercomputer. So about 2 weeks of that supercomputer were devoted to us and our stuff. So if you how many seconds is 2 weeks? No, it's not hard to figure out. How many seconds in a day? 36,400, I think, times 2 weeks. 509 times 10 to the 17th. How big are we now? Oh, come on, I don't want to count. 6, 9, 12, 15, 18, 21. So we can now start to do things in around 10 to the 21 is our limit. Does that make sense? We have 10 to the 21 computations. That's about what we can theorize or start thinking about doing. How many of these applications can be done in the 10 to the 21 range? How many of these numbers? That guy. How about all the rest? How many of these can we do? No. Do you think we're ever going to be able to do these anytime soon? This one, maybe. I'll give it a different color. Let's give it this guy. Maybe he'll show up soon. I know it reads terrible for you. But the idea is that there's only so many classes of problems that you can run on supercomputers, and there's a lot of classes of problems that will never run on supercomputers. Partially because the algorithm is a dumb idea in the first place. If you go to the supercomputer world and say, I want to run Bogosort, please. It's like, all right, well, you're going to pay for the power plant that's generating the power for these computers. Any questions on that so far? Yes?
So, what impact would switching over to using, say, quantum processing have on this sort of algorithm?
Quantum computing is not going to completely change everything we do. It's not like you're going to turn on the news and someone says, hey, we figured out quantum computing, and we just throw away all of our computers and laptops and switch to quantum processors. They don't just do things faster. They're like a coprocessor. They will do a very small subset of problems faster, and only those few problems faster. For most problems, our existing computers are the way to go. So it'll do things like, hey, I want to factor these really large numbers into its primes. And I go, well, what's that good for? Well, it breaks encryption. Public-private key encryption will be broken.
I was thinking for like, it would probably be useful for like brute force since it
Yeah, it'll handle some class of problems, but most will not. So quantum computing will change a few things, but won't change a lot of things. And that's if we can ever get it to work. There's a lot of people out there who think that, nope, it's just in practice. In theory, it's great. In practice, you just can't do it. Other questions? All right, let's jump to the homework assignment. I went a bit long. For the big O, we're going to come back to this. Know this. You should be able to very quickly identify. If I say, here's this kind of algorithm, you should be able to immediately say, oh, it's this big O notation. And you should be able, in your mind, know what other big O notations are worse and which ones are better. So you can put these things into a relative scale. We'll go over these again. Big O is really important. For the homework assignment, I want to give you, because we're not tired of linked lists yet, a linked list based hash table assignment. I talked about earlier giving you both the array-based and linked list-based assignment in one shot and we timed. That's too much to throw at you. I want to split it apart. We'll do a list-based one and then we can do an array-based one later. But we'll start with the list. Here's the gist of the assignment. I give you tests where I want you to create a hash table that accepts this kind of data. And for any key value pair, the keys will always be strings. Your job is to hash the string, figure out which bucket it goes to, and write it into the correct bucket, or retrieve it from the correct bucket. So Jazz should go in, is associated with the key of 6. That should go into the hash table, and then you should be able to retrieve the value out of the hash table. What's the value of 6? It should be Jazz. You know your good old square bracket code, you've seen that before. That should also retrieve 6. This one should overwrite Jazz with nuggets. This one should verify that something with a key of 6 exists. This one verifies that something with a key of 1, 2, 3, 4 does not exist. Remove removes the entry from the hash table, so it should no longer exist. These add in a bunch more teams. These verify that you can find them. These verify that you have 9 in your hash table. This one verifies that you didn't somehow put all of your data and cheat in one bucket. Sometimes people do that. Like, well, I could just really behind the scenes use a single array and just throw everything in one array and look it up in one array. Nope, this makes sure that I verify that you will never have more than 4 items in a bucket for that previous test. Then I throw in a lot more items, roughly about 10,000 items, and I do some more checks and verify they all show up. Then I do more. Instead of doing hashing putting strings in, I want to have a hash table of product objects, and I've defined a class product up above. So the idea is that I want to make a silly string product that costs $5, and I want to put that product in my hash table associated with this ID key. This product code is 12341, 51231. Hash that string, tells you where to go to find that bucket object, or where to put that particular product. More work. Go retrieve that object. Let's get the novelty foam hat. Let's put that in the hash table. And again, let's do a lot more. I do a big loop, and let's just throw in a whole bunch of made-up projects into the hash table just to see if it works. And then I verify that there's a lot in there, that we can find them all, and so on. Then I have some fun. Let's do a hash table of hash tables. Why do I want to do this? Here's a real-world example. These are storing homework assignment scores. Alice has done assignments 1, 2, and 4, but not assignment 3. Alice received the scores of 73, 65, and 91. Bob did 3 assignments, skipped assignment 2. Carl did all 4 assignments. I want to put that in the hash table and show that I can use the hash table to insert data and retrieve data. From a readability point of view, does that line of code make sense? Like, can you understand what it's supposed to do? In the student assignments hash table, go get something with the key Carl. That retrieves for me Carl's hash table. Alright, in Carl's hash table, I want to create an entry with a key of 4 and a value of 10. What if I want to go retrieve some of those entries? How do I retrieve that one? Alright, in the student assignments, go retrieve the Carl entry, and in that Carl entry, go retrieve the 4 entry. Is that highlighted line of code easy to understand? Is the under the hood really powerful and crazy? Yes. But this is why hash tables are awesome. So your job on the assignment is to do the following to-dos. I should not ignore online students here. You're right, Joseph. Nugget shouldn't overwrite the Jazz. I'm going to fix that. The Jazz will overwrite the Rockets. That sounds better. We are going to start with a array of linked lists. So you have to define an array of linked lists here. How do you do that? If I ask for an array of ints, how would you have declared an array of ints here? This is important. How would you have done it? Joseph says int some array square brackets. I would have done a little better. Int star ARR. Why did I do star and not a hard-coded array size? Actually, you know what? I'm nice to you here. I do make the array a fixed size. Your array will always be num buckets in size. So you can do it this way. Is that all right for you guys? So now, well, hold on. No, that's going to cause problems. Can I create an array that big on the stack? Maybe I can, maybe I can't. I think we'll be okay. It's only 10,000. It's not a billion. I think that'll all fit in the stack. But I don't want ints. What do I want it to be an array of? No. No. It's an array not of key value pairs. No. Everyone's wrong. I love it. It's an array of linked lists. Every linked list is a bucket. How many linked lists do I want? 10,000 linked lists. So how do I say an array of lists? So what do? Do I say an array of ints? No, what do I do here?
You put the class name.
I do an array of lists. In this case, I am going to use not our linked list. I am going to use the standard template libraries linked list. So we will use their list. Sound okay? Now, the list is templated. I can't just say I want an array of linked lists. It says, well, what data is the linked list holding? So what kind of data is the linked list holding? Do I need to go back and find that picture?
Node 3D objects.
Oh, these are ugly. Hopefully one of these will ring a bell. That's the array based. There's my... Here we are. I don't know if this rings a bell or not. The black is... Oh, no, come back. The black is the array. The red is the linked list object. Blue is the node. And what goes inside of the node? And this I didn't show very well. I actually have to show a little bit better. Inside of an individual node, here's what we'll do. I can't just stuff a key and a data in there because it's just a single piece of data. How do I fit two pieces of data in one piece of data? Does that make sense? How do I fit both a key? How do I cram both a key and my data into this field of the linked list? Can I put two items in one item? How? Wrap them in another object. What is this object? It will be a key value pair object, which I have nicely defined for you here. So what do I want a list of? Do I want a list of T's? No. I want a linked list where the nodes hold what? Key value pairs. Does that make sense? But the key value pairs are also templated. The key is always string, but I need to know what the data is. Do you remember how you had to do a shared pointer of a node of T's? What do I want here? A list of key value pairs of T's. You okay? Oh, this is going to get to be a mess. I almost just need to give this one to you. Are you okay of doing a list of key value pairs of T's? Yes, but I want to take it one step further. I want it to be a unique pointer. So we're going to go into the scary realm of triple templating. I want it to be a unique pointer holding an array of lists of key value pairs of T's. Can you go that far deep? This is the assignment that drives people crazy. Whether you should. Once you get the array declared, that's a lot of the battle. From here, you need to complete these methods: create, retrieve, operator square brackets, exists, remove. How do you run, say, the... We need to spend more time on this. I can get you this out the door for create, but I need to spend more time talking about retrieve, operator square brackets, and exists. This one will be a 2-weekend long assignment. Let's get you at least started on create. What's going to be the process for create? You're given a key and an item. Tell me in English, what do you do? It's a hash table. What's our process? There's going to be a lot of tools here. Think it all through step by step.
Mel needs to create a key value pair.
We'll need to create a key value pair to put our data. Okay, so I've got a key value pair object. Then what? What do I do with the key? I have to hash the key. Guess what? I've supplied for you a hash function already. So you hash the key. Does it even mod for you? Oh, it sure does. Look how nice that is. So this is a very simple hash function. I hash and I mod. Then what? How do I go to that bucket? What do I mean by a bucket? Nope, it's an array. So what can I do? I can just go straight to that. Yeah, square brackets. I just go straight to that index. Hey, my array, just go straight to that spot. Then what? Now I'm working with one specific list. So how do you push an item into a list? What's the list's insertion method? Push back. And what do you push back into the list? The key value pair object. You could do that in one line of code. This is an annoying assignment because I don't know how I can tell it to you. I can't write it out because I'm writing out the line of code. And once you figure out the line of code, you're like, oh, that's all it was. And then I have students getting mad because they spend 10 hours. I can't write a line of code. I know, but this is the most powerful line of code you'll ever write in this class. It's great. You don't have to. You can do it in separate steps, but it's actually fastest to do it in one step. So start with the create method. We'll talk with some of the others. If you want to figure out, you can do operator square brackets, but if you want to start getting into retrieve, exists, and remove, you have to figure out how do you use a linked list to get through these items. And what is this going on with the R values here? We'll talk about that more on Monday. Yes?
Start with the create method for L? Or
start with that one.
Okay.
If you do the L and you don't even implement this one, everything will fall back to the L method one.
Okay.
Does that make sense? We got a lot. I didn't realize this one's so hard. Yes, Jeff, this is supposed to have 2. It's an R value. It's just an R values. It's not a by value, it's not a by reference, it's a move. It's an R value. All right, I'll get this out the door. I understand. If you get started on some of it, I'll be happy. If you need more to wait until Monday, we can go over it then. Remaining time. Oh, I put it off to the end. I should have thrown a bunch of fake codes throughout a lecture. I'm getting lazy. I'm doing it at the end every single time. Let's pick out some numbers here. What would be some good numbers? I'll use this guy. 10, 10, 5, 4. Other questions for me? All right, let me come around and help you on the current homework assignment. Online students, just stick around, I'll help you.